In Part 20, I covered redox reactions. Electrochemical reactions are a form of redox reactions that utilize electricity to accomplish a specific reaction, to either produce electricity, such as a battery, to determine the concentration of an element, or to precipitate elements out of a solution. In this presentation, I will try to focus on the determination of species in a solution and its concentration using an electrochemical technique. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. In Part 20 A and B of this series, I mentioned the redox table, which showed the reduction potential voltage of the reactions of various compounds and elements. The standard reduction table is used in conjunction with the Nernst equation. It relates to the electrostatic fields in relationship to the ionic charge of an element or polyatomic compound. As shown, the reduction table gives the redox dissociation equation along with the standard cell potential in volts. This table can be searched and downloaded for free as a PDF copy for your reference. A common illustration of a cell is shown. It is comprised of two cells or two half cells, as will be discussed shortly. The Nernst equation itself can be quite confusing. The capital E in the equation is the total required voltage applied across the anode and the cathode of the complete cell. The E0 is the cell potential. It is important to realize that this voltage potential is the potential required to sustain a reaction under a stated condition, such as concentration at a particular atmospheric pressure. The capital R is the universal gas constant of 8.314 joules per mole at a particular temperature in Kelvin. This figure value never changes. T, of course, is the absolute temperature in Kelvin. It is the N in the equation that is often not understood. The standard reduction table gives that value. It is the number of electrons that is transferred during a given reaction. As shown in the graphic, aluminum 3 has 3 electrons that is transferred to reduce the aluminum ion to a stable pure aluminum ion that may be precipitated as a pure solid compound. The capital F is Faraday's constant. This too never changes. Based on electrical theory, it is equal to 96,485 coulombs per mole. For those not familiar with natural logarithms, In is the natural logarithm of the reaction equation Q. Q is simply the value of the product coefficient divided by the reaction coefficient. This too, in the context of the Nernst equation, is confusing. Remember that I had said that the standard cell potential, E0, is a condition statement. Q is the amount of unknown concentration of an element of interest in a sample to be analyzed. The total concentration of the unknown is the product coefficient. The total would then have the value of 1. The reaction is the amount of concentration that is reasonably used as the endpoint of the analysis. The most common value given is 10 to the minus 9. Therefore, the Nernst equation can be simplified. Without a total mathematical breakdown, the equation as shown where E equals E0 minus 0.0592 divided by N times the log of 1 divided by the element's concentration value M, N, which is shown. It must be somewhat understood that the solution, referred to as an electrolyte, has the ability or characteristic of passing an electrical current between the cathode and the anode when energized. The electrolyte itself must contain enough ions in solution to be able to be conductive. The solution becomes the wire in the circuit that is resistive. The potential across the electrodes must be high enough to start the reaction. Solutions containing strong acids such as nitric acid, hydrochloric acid, and sulfuric acids, having dissolved elements, that is, the metals of interest, this includes nonmetals, are electrolytic solutions. When the electrodes are energized with enough potential, the solubilized ions will start to migrate towards their oppositely charged electrode. Positive ions start to move towards the cathode, while negative charged ions start to move towards the positive anode. At the same time, an electrical current is established which resistively flows through the electrolyte, albeit small in amperage. Other solutions such as strong bases, for example sodium hydroxide and potassium hydroxides, are commonly used as electrolytes as salt bridges. This includes weak acids and bases. Examples would be acetic acid and ammonium nitrate solutions. Soluble ionic compounds of sodium chloride, potassium bromide, and magnesium chloride solutions all act as electrolytes. The migration of elements within an electrolyte solution is the basis for metallic plating techniques, as well as battery technologies, precipitative analysis, and electro-refining of metals. Knowing that the separation and migration of ions will result upon an applied voltage across the anode and cathode that is of a specific voltage. This is E in the Nernst equation, the total voltage between anode and cathode. There is also a voltage potential that is produced within, that is between the cathode and anode in the electrolyte solution, which is E0. This voltage can be detected by a reference electrode. Common reference electrodes are the calomel electrode or the silver chloride electrode. The basis for which these electrodes function is what is referred to as a salt bridge. A single cell can be divided into two sections, each of which is referred to as a half cell as shown. An electrolytic junction is placed between them. Using a salt bridge prevents a gaseous or chemical product that may be generated at one electrode from migrating to the other electrode and somewhat reacting prematurely. It would also block, that is, prevent the reduction of any oxidation product that would lower the efficiency of a single cell. The power supply across the cathode and anode forces not only oxidation and reduction, it causes an accumulation of ions at each electrode. The salt bridge essentially neutralizes the charge buildup on the electrodes. As the electrical charges would have built up, opposing electric fields would also build up, eventually stopping the electron flow and freezing the ion migration. The salt bridge facilitates a stable flow of current through the system. It also is used to separate different electrolytic solutions and can be a single ion absorbing membrane dividing a cell into two half cells. If the electrodes were of two different elements, such as one being copper and the other being silver, using an inert electrolyte such as potassium chloride, potassium nitrate, or sodium nitrate with equal ion transport numbers minimizes the potential buildup at the liquid junction, optimizing the cell's efficiency. Where the bridge contacts the solutions at each end of the bridge, a small voltage potential will develop. This is the principle to which a reference electrode works. If the electrode was placed into a single cell directly between the cathode and the anode, the voltage at that point of contact with the solution in the cell would register a voltage that at that point or location in the electrolyte. It is used to monitor and to adjust the voltage within the total cell as the reaction continues without any other premature reactions, such as co-precipitation of an element. A typical lab setup is shown in the illustration. There is a lot more that could be discussed in regards to how electrochemical analytical techniques work. What has been discussed so far is enough to be understood. There is a lot of manuals and articles, including videos that can be searched. However, the intent is not to have you become an expert on the subject, but as a small operating miner, prospector, or hobbyist, what you will need to know is how to adjust the cell voltages using the Nernst equation. Most, if not all, manuals and articles, including YouTube videos, do not fully explain how to use the Nernst equation in practice. Most only describe how the cell functions in relation to the chemical reactions that take place. Therefore, going forward, using practical examples, one should be able to conduct your own experiments in refining, recovery, and concentration analysis. The first example is precipitative, that is to say, a deposition example for the deposition of copper. It can be used for any other element in solution. Now this example pertains to a single element solution where copper 2 is precipitated, that is, deposited as a solid copper onto a solid copper cathode. For a solid deposition of a metal, the activity will always have the value of 1. One must not forget that the M, meaning the metal ion, is an assumed unknown starting concentration, or an endpoint concentration of the metal ion. In this deposition example, the endpoint concentration chosen is 1 part per million, or 10 to the minus 6. The reaction equation shows that N will equal 2, and the table shows that E0 is equal to 0.34 volts. We can now calculate what the voltage would be at the endpoint of the deposition. 1 divided by 10 to the minus 6 equals 1 million, and the log of 1 million will equal 6. And 0.0592 divided by 2 will equal 0.0296. Therefore, 0.34 minus 0.0296 multiplied by 6 will equal 0.162 volts. The starting voltage across the cell would be 0.34 volts. When the voltage drops to 0.162 volts, it would be reasonable to assume that all the copper would have been deposited onto the cathode. It must be noted, however, that the cathode is negative to the positive anode, and the start voltage would need to be adjusted and held to 0.162 volts to ensure that all of the copper is deposited onto the cathode and to ensure no other unwanted reaction takes place. The applied voltage must not be lower than 0.162 volts. As an application, in regards to this first example, in fire assay, the sample is combined with a flux material, it is melted, then cooled, the resulting bead is then compelled and parted. That bead, usually gold, would be placed into a parting cup with nitric acid added to remove any alloyed silver that may be present. Instead of discarding the solution, electrochemical deposition can be used to recover the silver by having it precipitate, that is, deposit on a thin, pure silver wire. Now, to know how much silver was deposited, the wire would have to be weighed first, prior to the deposition. In essence, silver from silver-plated scrap metal can also be recovered. There are times that you will need to separate species in a solution. Some samples and even scrap metal will contain both lead and copper. Note that the lead and the copper are both soluble in nitric acid. To stabilize the reaction and ion transfer, a salt bridge using potassium chloride should be used. 2 calculations will be needed, one for the copper and one for the lead. As shown, the copper starting voltage is 0.34 volts and held at 0.162 volts, while the lead starting voltage is 0.13 and held at 0.12. In practice, the lead would be the first to be separated while the copper is left in solution. Once the lead is plated out onto a pure lead wire, which is the cathode, it is replaced with a pure copper wire for the deposition of the remaining copper. The voltage would be readjusted to 0.34 volts and held at 0.162 volts. Here it should be noted that the lead wire is removed from the solution while the voltage is still applied. This eliminates the redissolvement of lead back into solution that may occur during removal. Once removed, the power is disconnected and the copper cathode is exchanged. This procedure is the same for the removal of the copper wire cathode. Within the solution, there is a flow of electrons from the negative side of the power supply towards the positive side of the power supply. At the same time, there is a migration of positive ions migrating that is flowing to the negative cathode, while the negative ions flow towards the positive anode. An excess of negative ions are derived from the solution and the salt bridge if one is present. As the positive ions are depleted, that is deposited on the cathode, the resistance of the solution increases and the flow of electrons decreases while the positive ion potential diminishes within the solution. There is also a space very close to the electrodes where the ions start to accumulate. As shown, the positive ions start to build up an opposing field. This is the boundary junction. The voltage must be higher than the opposing ion potential for the remaining ions to completely deposit onto the cathode. The extra voltage potential is referred to as the overpotential. As the ions become depleted, the resistance and current follows Ohm's law. The overvoltage to keep the minimum voltage required for total deposition without interference, the supply voltage will have to be adjusted. As the supply potential is initially set against the total resistance of the electrolyte containing the ions in solution, the drop in the ions dramatically increases the total resistance of the electrolyte. The supply voltage will need to be adjusted. This is the required overpotential. In essence, by adjusting the supply potential takes into account the consideration of the needed overpotential. The values shown are arbitrary and are used to demonstrate this phenomenon. If Ohm's law was the only consideration, the voltage would have stayed the same. Current would have decreased as the resistance increased. However, the ion depletion becomes a factor in the solution's total resistance. Since the voltage is equal to the current in amperes multiplied by the resistance, it is easy to understand that the supply voltage would need to be adjusted to remain in the theoretical limits for total deposition without interference. Using a reference electrode allows for the precise control of the cell potential in respect to the working electrode. It is advantageous to ensure that the target element, that is, the element of interest, is deposited without unwanted side reactions. This not only enables total deposition, but allows for a quantitative determination, that is, how much was actually deposited. It not only allows for a stable voltage baseline, it compensates for the IR drop of the solution. The cheapest reference electrode is a graphite rod. However, there are a number of reference electrodes that can be purchased, such as a silver-silver chloride electrode, a standard hydrogen electrode, and a calomel electrode. Now, these electrodes have fixed voltage potentials. A graphite rod may be used as a reference electrode. However, graphite is non-reactive but will have an electrical resistive property to it, where the manufactured electrodes such as the calomel, the silver chloride, and the standard hydrogen reference electrodes will have a fixed voltage characteristic to them. For a graphite electrode, some experimentation will be required. Now consider the deposition of nickel from a sample solution using a silver chloride electrode. The unknown concentration is measured to be roughly 1 molar. That's assumed. E0 equals 0.236 volts. The silver chloride potential is 0.197 volts, and that's fixed. The E measured equals E, where E is the total applied voltage across a cell, calculated as 0.236 volts. Therefore, E minus the E reference equals the voltmeter reading. In this example, the voltmeter theoretical reading should be 0.039 volts. Now in practice, the ammeter is used to measure the current in the system. To set the start voltage, you would slowly sweep the voltage downward from a point slightly above theoretical to a point where the ammeter spikes in relation to the applied voltage. This would be your starting point. By keeping the reference voltage constant as the element deposits to endpoint, the current will drop. Where the current no longer changes will be the endpoint. As I have mentioned, there are a few reference electrodes that can be purchased. The most commonly used are the standard hydrogen electrode, the silver-silver chloride electrode, and the calomel electrode. There is also a normal hydrogen electrode. Now it must be noted that these two electrodes do not have any fixed voltage. Therefore, any reference to a fixed voltage is 0 volts. The table shown lists the more common electrodes. Note that the fixed voltages are in reference to the hydrogen electrodes. Unlikely though, if you had to convert between reference electrodes, the formula to do so is the E1, which equals E2 plus E reference 2 minus E reference 1. Well, as an example, if for some reason you needed to know what your reading is against a silver-silver chloride electrode, one that is saturated with an internal potassium chloride solution, and your reading was 0.500 volts, the voltage for the standard hydrogen electrode would be the 0.500 volts plus the 0.197 volts of the fixed silver chloride electrode minus the 0 volts of the standard hydrogen electrode. This would equal to 0.697 volts as shown. To set up a small home electrogravimetric lab, there are a few pieces of equipment and material that will be needed. A fairly stable DC variable 30-volt power supply and an ammeter to monitor the amperage in the circuit. A stand assembly to be able to lower the beaker away from the electrodes when the endpoint is reached, as well as holding the electrodes in the sample solution. The clamps used to hold the electrodes should be insulated. To heat the solution to the required temperature of approximately 25 degrees centigrade, a hot plate is required. One that has a magnetic stirrer is suggested to keep the solution well stirred during the deposition of the element in question. These usually come with a thermometer attached. A set of beakers to hold your sample solutions and some salt bridges if your cells are divided into two half cells versus a single cell. For the cathodes, which are called indicator or working electrodes, can be pure elemental foils or wire, such as the copper foil or the pure gold wire as shown. I prefer the foils. Elemental rods may be used, keeping in mind that they should be of the same composition of the element that is being deposited. If silver is to be deposited, then that cathode, that is your working electrode, should be silver for easy refining. The graphite or carbon rods can be used as anodes, being your counter electrodes, or they may be reference electrodes. Now these may be purchased with terminals attached for easy connectivity or without. Clamps will be required. Now these electrodes may be any other metallic rod as long as they do not interact with the solution, resulting in the unwanted reactions. My choice would be to purchase a silver-silver chloride electrode or calomel electrode as a reference electrode, allowing for better precision and efficiency. Additional supplies include acids, most commonly used as hydrochloric acid, nitric acid, sulfuric acid, and acetic acid. Sodium chloride, potassium chloride, ammonium nitrate, potassium nitrate, and silver nitrate will also be needed. The picture displayed is a basic setup. Feel free to experiment, but notice the main components: the power supply, the hot plate, the beaker, the ammeters, and in this case 2 electrodes, which are the working electrode being the cathode and the counter electrode, which is the anode. In this presentation, I hopefully gave you some valuable information in regards to electrogravimetric analysis and metal refining. I purposely left out a lot more theory and hope that this presentation entices you to research more on the topic. What I tried to focus on is the calculations that permits the estimation of the voltages required to start the reactions that will separate and deposit the desired elements in the sample. It was my intention to present this presentation in a form that would allow any small-scale miner, prospector, and/or hobbyist to understand the practical side of electrogravimetric analysis. The presentation concludes this series. And if you found this presentation useful and/or interesting, or if you know someone that would benefit from this presentation, please forward or share, give it a thumbs up, and subscribe. If you have any questions, reach out and I will endeavor to reply. Now, it may take some time as most of my projects are off-grid, so please be patient. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.